today, again, we're lucky to have another great guest lecture from Goodfire, Jack Merullo. He just graduated from Brown, so he might not be the oldest. Some of you might be older than him, actually. But anyways, so yeah, he actually taught an interpretability course at Brown before he graduated, just on his own. And yeah, now he's a Goodfire, and he'll tell us about what he's doing there.
Cool, thanks. Yeah, very happy to be here. Thanks, everyone. Thanks, Surya, for having me. So you guys have been talking a bit about circuits in models recently, so I wanted to talk a bit about the kind of like patterns that we find and abstractions that we can like pull out of doing that kind of really low level analysis, and talk a bit about like what we can do with that and what we learn about models. So I guess to start, I want to pose like, you know, what should interpretability be able to give us? Like, what should we learn about models by doing interpretability? So not necessarily like what should we use interpretability for, but like what information do we get from actually doing this? And in my opinion, like, and this isn't a universally held opinion, is that we should be able to like distill some like higher level understanding of like how models do anything, like how they like to behave, how they like to implement things, etc. So I don't think it's enough to say like, you know, we can explain any given input by like, okay, these neurons are connecting, and like we have some, you know, sense of kind of semantically what's happening, but it's all kind of like jumbled up. I think it's much nicer to have like nice abstractions over what we think like models do when they're solving tasks. And then, you know, contrasting this with like what do we actually get from doing interpret, like what do we get? Some people would maybe argue like we just get this big bag of like disparate results on little bits of understanding that don't really relate to each other. I like this GPT image that I got to describe this. But basically, like under this view, like these findings are all like kind of piecemeal and unrelated, and we're not really headed towards like any greater understanding of the model. And we're just kind of like spinning our wheels, picking up little nuggets here and there. And yeah, under this view, like I would argue we're really not much better off than just with like a full uninterpreted model. Maybe we have tools that allow us to like better control them or monitor them, but like I think it's much more interesting to think about like, you know, we haven't had anything that's so coherently able to use language before. It would be great to pick it apart and understand what's going on under the hood, how it's acquired language, how it's similar or different from humans, et cetera. There's so many questions there that I think are worth answering. And so my argument here is that like when we are doing interpretability specifically at like the low level of like circuits, we are like getting actual like sort of algorithmic primitives that models tend to learn that show up across models that are, you know, pressures from the training data and that are used to solve like various types of tasks. So we are getting a sort of like distilled picture of what's going on. And we keep finding these, and they're general, and like we can kind of compose them together in interesting ways. And they give us a real foothold for like real understanding, basically. And I think an important part of this is kind of building our mental model of like what kind of program, for example, a transformer language model is, or like any model that we're considering studying. And I will point out that this is like sometimes implicitly made by papers in the field, or maybe more explicitly, usually relating language models to, or any model again, to like, you know, kind of familiar data structures. So I'll show a few examples. This is the Rome paper, which I think you all read, where they are, you know, replacing facts in a language model. So let's say editing weights so that the model thinks that the Space Needle is in Paris, for example. This is a view that language models are mutable knowledge bases, at least part of them are. The induction heads paper, induction heads themselves and attention is a read and write register. This one's like a little on the nose. The MLPs in transformers are key value stores. So So this is like a kind of like, these abstractions are like appealing to us as researchers, and they help people explain their work, and like I would say that we are like headed towards that kind of understanding from doing interpretability. So just to outline what I'm going to be talking about a bit, I'm going to quickly just review like induction heads, which I think we all know, but I think they're like a great example of what I mean by a computational motif. I'm going to talk about the indirect objects identification circuit, which is a very well-known circuit from like a few years ago, like 2022/2023. Go over a bunch of more motifs, pointers to the literature that I think are just really interesting, and then challenges, open problems, future work, etc. Cool. So induction heads, these are attention heads in transformers in autoregressive models that are like specialized, like pretty much purely for doing pattern matching and pattern retrieval from context. So if you give the model text like ABC, ABC, AB, blank, the model is going to be able to predict C. One way that it's able to do this is through induction heads, which you would attend from the B token to the last C token. So this is the last token that followed the last B in the pattern. And you're able to like move that information over to the B token in order to predict C as the next token. So I'm writing attention here. So B is attending to C, but the flow of information is like forward in the sequence. And we don't need to get into the like implementation details, but I have some slides for it if people have questions. This is kind of like the canonical implementation. There's many ways that a model could actually implement an induction head. That part's not super important, but this is I think the most well-known one. And the important thing is that it's like a composition between two layers, either connected or like across multiple layers, where positional information is kind of always being passed along, and then the actual induction head notices a pattern and is able to retrieve, using the positional information, the next token. So I'm going to skip this for now, but yeah, please. Oh, and please interrupt if you have questions at any point. But the point I want to make is that, like, in the in context learning and induction heads paper, the authors like suggest that there are natural ways in which induction heads like could be repurposed for in-context learning more generally, or just a bunch of different tasks. And this is exactly like the kind of thing I mean, which is that there are simple mechanisms like in these models that are like able to be like repurposed and show up like again and again. And I think maybe one way to like point that out is if I just searched induction head language model on Google Scholar, and there's like 400 papers about induction heads. So people have found induction heads in all kinds of things, found them to be like really interesting things to study. I think this like supports that point. Yeah, good place to stop real quick if there's any definitional questions, but otherwise I'm just going to move on to the indirect object circuit. Cool. So before I really get into that, I just want to quickly like informally go over circuit analysis, which there's a few ways of doing it, but broadly, if you view like a language model as like a graph and like components as nodes and like information flowing from nodes to other nodes through these edges, a circuit is like the path through this graph that's like passing the important information needed to like make a prediction. So the kind of thing where if you were to like ablate away all these like unused nodes, like the prediction wouldn't change much, up to some degree. And the point of this is that it like lets us causally reverse engineer like what a model is doing when it makes a prediction. So you guys heard about this when Atticus came to give his talk. Similar methods like used there from there. And like common criticisms for circuit analysis are like, okay, so you found a circuit that does X, Y, or Z, like who cares? Like if every little behavior has its own circuit, like we don't actually get closer to any level of understanding. We don't really care about, as you'll see, like the indirect object identification task very much. It's like one of many things that language models can do. But what we really want are like algorithmic building blocks, general purpose mechanisms, kind of like induction head type things, but like for all behaviors. And the argument I'm making is that circuits can be like content independent and generalize in the way that we care about. So here is the IOI circuit from this paper, Interpretability in the Wild, which first iteration was in 2022. And it's like still widely cited and used for like toy tasks and stuff. So I think it's really worth knowing. And I'll go through some of these parts, some in more detail than others. But basically the algorithm like breaks down into like 3 steps. First I should talk about the task is basically it's all sentences like, John and Mary went to the store, John gave a drink to blank. And the model has to predict the next token. The surface level details change a lot, but it's all like this kind of like 2-sentence structure. And you're predicting an indirect object. Here the indirect object the intended indirect object is Mary, like to Mary. And there's like a bunch of things that you could like continue this sentence with. Like you could say like, gave a drink to me, gave a drink to you, whatever. But like for the purposes of this analysis, the authors just cared about like, how does the model know that the logit for Mary should be higher than the logit for John? Because John gave a drink to John makes no sense. So it's like a really, really simple behavior, but even understanding how models do this is a kind of Herculean task. So the algorithm, like in like broad detail, what that they find is, I think, kind of interesting. So the model first recognizes that there are 2 Johns, like it recognizes like duplicate names. And then when it comes time to like, it's just kind of storing that information like in its attention cache. And then when it comes time to actually predict the name, it kind of uses this information to say, okay, there's kind of a lot of Johns here. I probably don't want to say John again. But it's not actually like making a prediction at that point. And it passes that information, like inhibit John, to this like dumb mechanism, which just attends wherever it attends, it'll copy that token. So if it attends to Mary, it'll copy Mary and then produce Mary or promote Mary in the logits. And since John is inhibited, it will attend less to John. Cool. So one thing to note about this circuit is this duplicate part, which seems kind of fickle. So for example, if I gave you a new prompt, John Mary went to the store, and I inserted this sentence in the middle, Mary was having a great time, John gave a drink to blank. Now John and Mary are like they both appear twice, like they're both duplicated. And the circuit no longer explains this behavior. So this is an example from the paper. They talk about this. So they're very thorough in their analysis, and they point out these places where things can differ. But like, this isn't great, right? Like, so we're not really explaining indirect object identification anymore. Like, the circuit is like very descriptive and it's correct, but like, what exactly are we explaining? Are we explaining exactly this data set, which is like this weird kind of synthetic 2-sentence structure? So if we have to do this for like every behavior, like every little prompt like changes in this way, like it's so over basically. Like interpretability is screwed, like because we just don't learn anything about the model. Like, if the Wang et al. Circuit is this like tiny part of predicting an indirect object, then that's terrible. So this was a question I had during my PhD that I wanted to look at is like, well, do other tasks use like a similar circuit? It doesn't have to be indirect object identification. Like all these like functional parts like seem totally legit and like totally general purpose. Like surely, they're used all the time to do stuff, right? Like induction heads, for example, are used all the time. Like, is there a broader picture there? And so that, I was just like looking at data sets. I was looking at Big Bench, which has like hundreds of like kind of synthetic tasks. And this one stood out to me, which is the colored objects task. For the purposes of this work, I changed it a little bit from the original. But the main idea is to just list a bunch of like colored objects, like blue pencil, black necklace, yellow lighter. What color is the pencil? So it's like similarly very easy, I think, to the IOI task, and it has a kind of similar structure where there's like retrieval from context, right? And so maybe there's like some big overlap between these two circuits. I wasn't really sure exactly when we were working on this, but I think you can see that like similarities there in what's required. But before I want to talk about that task, I want to like maybe step back and like mechanistically walk through the circuit in IOI a little bit more, so that we can understand like kind of what we're looking for. Yeah, I'll do that. So kind of moving backwards now through the circuit. So we're going to focus on this last part, just the name mover heads. There are a couple like other categories here, but we just care about the name mover heads right now. So like I explained, like there these attention heads so this is in GPT-2 small. We replicated it in GPT-2 medium just because it was a little bit of a better model. But they showed up there too, which is these are just attention heads that whatever they attend to, they're going to copy it. They're going to promote what they attend to in the logits. So if you like aim it at Mary or John, it'll promote John or Mary. Skipping that. And then the thing that tells them like what to attend to, like where to point the query in the attention mechanism when you're doing the query and key matching, are these inhibition heads. These attend from the last token to the duplicated token, so John. So it's like, all right, I'm noticing some Johns. Let's like send a signal so that later on that the mover head doesn't attend to that, to either of them. So this is just visualizing no inhibition versus with inhibition. I think you get the point. The mover head attends less to John as a result. Another view of it, so this is like a signal that travels like up the residual stream to some mover head, a couple layers down the line. Cool. That makes sense. Cool. Yeah, so I think that's the most important part of this circuit, actually. There's that earlier part with the induction heads and the duplicate token heads, which I kind of mentioned. Those are just passing like positional information, basically. And again, another instance of induction heads like doing something, not exact pattern matching, basically. Cool. So now we do path patching on both of these tasks, IOI and colored objects. This is like, so from Atticus's lecture, I don't know if you talked about path patching, but it's most similar to causal mediation analysis, which I'm pretty sure came up. And so we're trying to find like direct effects on from earlier components to later components. So this just requires a lot of like counterfactual interventions. And sort of in a nutshell, like without getting into too much detail, what we found is that there's like a lot of similarity between these two circuits for these tasks, doing like context retrieval, with one very different part in the middle. The main one being that in the colored objects task, there's no activation of the inhibition heads, or there is, but they're not like causally implicated in this circuit for making the colored object predictions. And I think what's interesting is that the places where they're different are kind of like overlapping in the layers. So there's like maybe a bit of like crowdedness that's not able to use both, but our kind of like naive like overlap metric, we kind of like throughout that the number, like about 78% of the circuits overlap, like they're about the same, just with like a couple differences, particularly in the like inhibition heads, not activating in the colored objects task. So here they are again, in case you missed it. So this is the kind of signal that's not showing up. So an important thing to note is that the model that we tested this on actually doesn't do that well on colored objects. We tried to kind of find a model that was small enough but that we could do this analysis, but big enough that it could do something on this task. GPT-2 small couldn't do it. It was at random. But the important thing is that, and I maybe didn't mention this, but we give an in-context example just to demonstrate like what the output answer should look like. And it just helps the model be a little bit more right. The model only ever picks like these 3 colors, so it's like, okay, it's like that's not nothing, right? But maybe it's just having trouble. It's like running into heuristics. It can't pick like the exact right one all the time. For example, I found an attention head that like if the word orange was one of the colors, like this attention head just loved copying orange. I don't know why. Just transformers doing transformer things. But like maybe like something that would like help this model is actually like inhibition. Like inhibiting these would actually be really good, because it seems like they're slipping through just due to this kind of like random noise and heuristics and stuff. So we did this intervention where we like pretty much artificially just changed the attention patterns of the inhibition heads, which before weren't really doing anything in the circuit. They were just kind of like pointing like over here or like at these colors, which is, I guess, a useful thing to inhibit if that's what they're doing. But if we kind of like aim them properly, we can like kind of like fix the, like repair the model on this task. So it jumps up from like around 50% to like 94% after doing a couple like selected head interventions. And it doesn't just like increase the accuracy, which is nice, but all the other signals that you can kind of test for. So it's like, are we now like kind of mimicking the behavior of the IOI circuit by doing this? So like the mover head attention goes down on the incorrect answers. That's like what the inhibition heads do in the IOI task, et cetera, et cetera. So we saw all those signals. So basically, like the point we wanted to make here is that like models can share like circuit components across seemingly like unrelated tasks, and like the number of circuits is like distinctly less than like the number of possible things you could put in this model. Basically, we can like distill down these models into like more simple like building blocks. And so some follow-up work with that, we looked at these inhibition as more. Oh yeah, is there a question?
I just have a question. If you train GPT, like say you really overtrain GPT-2, do you see performance increases on that particular benchmark? And then can you attribute like the performance increases or not to that circuit that you found inside of the model?
So we didn't try that. So basically your question is like, if you train the model, so if you train the model on the task, yes, the model would get like better. But your question is like, would it like strengthen this circuit? Like, would it repair the circuit? Yeah, we didn't try that. I could point you to some like really interesting follow-up work. Sorry, not follow-up work. Just other like circuit analysis work that came out later on from another lab on what fine-tuning does to like 2 circuits like this. And they don't look at the specific example that you're kind of talking about where like they look for a circuit being kind of repaired. But what they do find is that when you fine-tune on a task, like existing circuits that are already there like are strengthened. So yeah, basically it's not like fine-tuning doesn't seem to like invent new circuits out of thin air.
I think my question was maybe motivated more by rather than fine-tuning scaling, so both on the training and like the parameters of access. Like I'm curious if there's some intuition you can get from this about why either of those axes actually like improves the behavior of the model more. But maybe that's too general a question for this particular.
No, I think it's a good question. I can answer that like partially because yeah. So if you were to scale I'll stick with model size. There's a couple things like I can talk about here, which is, so in case this is like kind of unclear, this is like a kind of like subset of the flow through the model layers. So there's like layer 11, layer 12, 13. And something that we noticed and like kind of anecdotally in like other settings is that when attention heads are like, when the signals are kind of like packed, the layers can, like, we think there's like, since you're just like moving forward in the layers, if you don't like, if you aren't prepared to like pass a signal to, for example, like layer 12 here, like this attention head, you just miss your shot. And you just keep going, and then you like maybe miss the prediction because you missed this head. So a little bit of a roundabout way of saying, like, if you have a larger model, and we looked at this too in this paper, like GPT-2 XL, for example, you just get way more of every type of head, and they're a little bit more distributed. So you have more of a shot of, like, there's like redundancy to some extent of these mechanisms. And I think that like how generally we can like make that statement, I don't really know, but like, yeah, so there's at least some explanation there, which is like you have more chances to like execute the behavior in the forward pass. So that's one thing we noticed with that. Yeah, yeah.
Yeah, I'm curious on the task where you like modify the attention heads to get better performance on the color matching task. Have you seen like then worse performance on other benchmarks? Like, is it okay? Well, the model learned a sort of bad head for this task, but it was actually necessary for all these other tasks.
Yeah, I think there's like no free lunch. So there's like something a little synthetic about the intervention that we did, which is like it's not like actually clear how we would make the intervention and then go generalize it to like a new task, just because we're like actually just like kind of fixing the attention patterns. So it would screw up other things in that way. If we had a little bit of a smarter intervention that was like maybe something more like just turn on the like be more willing to just like fire the signal into the inhibition heads. Yeah, we might screw up some tasks, like we might overly inhibit something. But I think generally, yeah, there's like no free lunch, especially with making model edits, just broadly. I think generally good advice in deep learning is like do not fight gradient descent. Just like whatever the model figures out is going to be probably better than what you're planning on putting into it anyways. Kind of, bitter lesson-esque there. I saw another hand. Yeah.
It's kind of answered, but just for clarification, so for the colored object task, like it has the conflict gathers instead of the, or it does have the information heads, but it's not like causally relevant in the moment to the task, right? And then what your intervention is making the heads like causally relevant, like suppressing orange, purple, whatever the other colors are creating. And then, so basically the point is that like you're using a certain component of the IOI circuit to boost the performance of another circuit. Is that essentially what you're
Yeah, pretty much. Yeah, that's a good way of summarizing it. Okay. So our intervention is like, on one hand, like very gentle, like it's like a very small intervention, but on the other hand, it's like kind of on the nose, like we're letting the heads do whatever they want to do. We're just telling them like where to do it, like pointing them like which value vectors to basically like retrieve into the. Sorry, I should pull up the task here to show you. So when you're answering the question, basically like. Inhibit, like put the inhibition attention on these colors. Yeah.
Well, in that sense, you're putting that in because you know the answer, right?
Yes.
You're not putting it in on some sort of conditional way or some sort of automatic way.
Yeah, the point. Yeah, that's right. Yeah, the point here is that this very like unrelated task, the IOI task, tells us something about like how the model implements something like inhibition, and then that we can. Like use that to like these things like generalize. Basically, we can compose this like tool that the model has, which is this will pass inhibition to these later heads. We can like leverage that.
Okay, so are you saying you put in the answer to an earlier and it complicates and
Well, we're not putting in the answer though.
Okay, I'm probably missed what you said about this. But when you say you're going to do the wrong answers here.
Yeah, we're not.
Doing it based on obvious knowledge
Yeah.
of regarding organisms, or you're doing it in some sort of more principled way?
What would be a more principled way?
Um, I'm not saying, okay. It's getting it wrong for some reason.
Yeah.
Right? And if it inhibited the wrong answers, it would be better. So I understand that.
Yeah. Okay, so I see what you're saying. There's like so I think the important thing is, like we could like just, there's like the really like stupid thing you could do, which is subtract the like black and, black and yellow like logit vectors from the residual stream or something, and that's just like, the model's like not going to be able to predict these tokens anymore. Yeah, we could just steer them, and that's like not interesting. There's like, this is a very like artificial kind of intervention where we're like, yes, we know that these are the wrong answers, but we're telling the model not that you cannot predict black and yellow, but that like we want to like kind of like nudge this mechanism that we think indirectly interacts with the final answer. Like if you were to do the thing that we think you do, you should interact with this head, which then interacts with the logits, or these heads. So we're going for like a more indirect, like can you recover the rest of the circuit basically by just repairing this one little part.
Okay, I think I understand.
Yeah, and that's measured. Here, I think this is the really important one, which is, so accuracy is yes, we get it right, but it has the like causal effect on the rest of the circuit that we want to see. So in a follow-up paper to this, I thought the inhibition heads were like really interesting, and we just took a deeper look on how this. Let me go back for a second. This specific computation happens. So the fact that there is a signal being passed from this head up the residual stream to another head is, I think, a really interesting phenomenon. And we looked at like how actually that's like implemented, and we were able to find a like low rank subspace populated by like written into by the inhibition heads like collectively in GPT-2 small, that basically controls in a very general sense attention related to like items in a list. So what we showed is that like for any growing number of lists, you can kind of like move around this 3D space, and you'll like adjust which item in the list that you're attending to with the mover heads from the IOI circuit. And we could use this to find like, so it's mostly in the appendix of this paper, but like there are a lot of examples I think of like really interesting behaviors here. So like the inhibition heads are firing to prevent copying of like items that you saw previously in a list. It fires on like Oxford commas. It kind of controls like generation of like the and after a comma, and like things like that, just generally. And yeah, I thought that was very cool. And here's an example. This actually helped us explain a common language modeling error. So if you've heard of like the lost in the middle error, I think there's a paper with that name. So language models have a lot of trouble retrieving items from lists when they're like in the middle of a long list. They have like a primacy and recency bias. And we're able to mechanistically show like in this 3D subspace, here's like an area, and I'm not expecting this to be like super clear from this image, but like, because I want to move on, but so this, each color is like the probability of retrieving item 1, item 2, item 3 from the list. And as we add more items up to like 20 objects, so this is still like item 1, and then all the items in the middle, like, you know, like 5 to 17 or something, like all cluster in here. And so there's actually a nice geometric picture for like why do models have trouble retrieving these items, or why are they like imprecise when we're calling stuff from the middle. And we can show it's because they have trouble like very precisely navigating this small space. This is actually a 4D subspace, but one of the dimensions doesn't matter as much, so it's just easier to show 3. And so I think this is a nice example of like, okay, we started with the IOI paper 3 years ago on this like very simple indirect object identification task, and we can use lessons from that to make predictions about like new models. So the colored objects was on a different GPU2, and new tasks and like different behaviors just generally. So these are all kind of like distilling down to a kind of like nice picture of like the kinds of things like models like to implement. Yeah.
Can you go back one slide?
Oops.
Yeah. Can you maybe comment on like what exactly you gained then from, so on the one hand you say, okay, well like this is mechanistically explained error. Like why do they have trouble proving items from the list? You could have also then just like picked down the question like, well, why do they get really clustered or packed?
Yeah.
Right, so it's sort of like a question like inference model performance is still there.
Yep. I think, yeah, that's a great question. I think what do we do with this? There's I think a number of things, but I think like so I kicked these slides out. I thought I'd have a little less time, but one thing we'd like to be able to do is like, okay, this is like this is like a family of so this is a behavior that affects like a family of tasks and stuff. And so if we notice that our model is doing this, we can design, again, going back to like fighting gradient descent, just don't. But you can design training data that like targets this kind of like representational, I guess, like weak spot. So you can behaviorally measure these things too, but I think like when you know like why something's happening, you can make better predictions about like other things that it will struggle with. So extending from IOI to colored objects to like Oxford commas, et cetera, like that is not like a trivial jump, I don't think, to make just from looking at language model generation. So I think like this distilled picture about like how models are actually going to do this is interesting. But I would also say that like I am not like completely married to the idea that this needs to be used to improve models. I think this is like a worthwhile endeavor just for the sake of understanding how these models do things. But yeah, good question.
Can you say again how the space is defined?
Yeah, I didn't say, but I would love to talk about it. So we have, let me go back. Let's say, so we're looking at these inhibition heads now. Each of these inhibition heads is contributing some amount of signal about like inhibit John or whatever. What we did in this paper was we took the singular value decomposition of the weights themselves in these heads. And then what we found was that each one, like the signal for doing inhibition is actually extremely concentrated in the singular value spectrum. So you can actually distill the inhibition signal to effectively like a one-dimensional space so actually let me draw it this way, which is that each one of these heads is outputting like a one-dimensional output, like a scalar along some direction. This is represented as some direction in the residual stream, and this is what travels up the residual stream to the mover head. So it's a very compressed representation, like telling the model to suppress actually a positional encoding in the model. And so what we're graphing here is, again, this is the singular vector scale along that direction. So the direction we're talking about is corresponds to a singular vector from the weight matrix. And we're basically just scaling up and down along this direction for 3 of the heads. So this is the one from head 8.10, so layer 8 head 10, layer 8 head 6, layer 7 head 9. The one we're missing is layer 7 head 3, but it doesn't matter so much. And yeah, these are this basically forms the basis that we're talking about here. Cool. Yeah.
I guess it's interesting to me that, in some sense, this mechanism is wrong always, because right, there's no sort of parsing of the actual language in some sense if you're just sort of looking through a list of objects and then inhibiting ones based on a heuristic. So, I mean, I'm curious if like this is a thing that goes away as you see more and more complicated models, or if you sort of are always kind of doing a mix of right and wrong.
Yeah. Okay.
Maybe that was a sort of that was too much of a value judgment about what was right and wrong. But it seems like it wouldn't be what you'd expect from a system that was sort of doing the task in a generalizable way.
Yeah, totally. Wait, I want to make sure I understand what you mean by right and wrong. It's okay if it's kind of a value judgment, but you think that like you would say that there's probably like a more right way of implementing selection from a list and a wrong way, and this way is perhaps wrong because it gets like these like it doesn't generalize well. Is that the point?
I guess more on the sort of the like with the sentence example with John and Mary, you would expect there's some kind of semantic content that is actually embedded in that sentence that you could deduce that John is giving this to Mary sort of regardless of the whether or not the Mary's and John's relative positions in the sentence, and you could extend that semantic understanding to longer and longer sentences. Whereas if you're just kind of selectively inhibiting, like, I'm not going to give it to John because I know I'm John, so that's wrong. That seems like in some sense, the wrong strategy for that semantic task.
Yeah, because you'd think maybe like we have ideas about how humans parse these sentences. This whole project, the interpretability, like from the Wong et al. Paper, like is the indirect object identification. Like they I think probably had some expectation. Oh, we're doing like a syntactic parsing type of like circuit, right? Like how does the model like resolve this like parse tree basically, or something like that. But it's not doing that. It's using something like kind of stupider. I think that's really interesting to think about because I think it does kind of like like for exact like examples like that, it's fun to think about like how language models differ from maybe how humans implement it, or maybe like we perhaps are wrong about humans implement it. I don't know. And then B, like, do we expect larger models? I think this is the other part of your question. Like, do we expect more sophisticated models than GPT-2 small, which came out in like 6 years ago or something, and is like 125 million parameters? Surely we've moved on from that like level of mechanism. I think that's a good question, but I don't know the answer to it. There's a lot of evidence if you look at like universality of mechanisms in models, that you do see like a lot of similar mechanisms in small and large models, or even like features, but they are getting more and more sophisticated as they get larger. So I think it's a great open question on like what exactly, like with something like this, like how different does it look in a bigger model? I wish I had a better answer to that. I don't know if anyone has a better answer to that though. Maybe.
So nobody's looked at indirect objects in larger models?
So there's a paper on, the point of the paper was to look at the formation of this circuit over the course of pre-training. So they used the Pythia models, which have checkpoints available. And I think they might have gone, like there's also like a 12 billion parameter Pythia model. And I don't think they did that one, but I can't remember how big they went. It feels like probably like someone should have, right? Like this is probably something someone would check. I can't think of it off the top of my head though. Yeah, good questions. I think really interesting. So I'm going to quickly go over some other examples, I think, of like interesting computational motifs that models learn. I just think it's really cool that language models learn these like really rich structures at all from like unsupervised data. and without any like explicit inductive bias to do that. Another attention head based one are successor heads. So these are heads that show up like all the time, are probably in the biggest and some of the smallest models. And they represent all of these concepts like Monday, like so days of the week, days of the month, months of the year, like first, second, third, ABC, numerals, etc. These all are like defined under like, are unified under like natural orderings. And there's one circuit, or at least one type of circuit, perhaps redundantly implemented, that will like retrieve the next item in that sequence. So this is a little bit different from like, next item in a sequence in like an induction head case, because this is like more like retrieving like parametrically, like from memory, rather than like from the context. Yeah, really interesting paper. I'd recommend checking it out if you haven't. This is another good one on the extended positional embedding in models. So this is another GPT-2 and co result where models are representing kind of like their own positional representation internally for like relative position and separate from like the kind of like hard-coded like rope embedding or like just absolute positional embedding. And they're using this kind of representation in previous token heads, which look in the like one token back, right? So just interesting that it would represent position this way. And I think you guys maybe heard from Emmanuel on the line breaking paper that came out recently. Is that right? Yeah, they cite this paper heavily in that because they find it similar kind of like concept. So I think this one's just really interesting. Another good helix, definitely in my like top 2 helices in language models. Not yet, but maybe top 3. That's so. This is from a recent paper looking at how language models do arithmetic, and basically they find this like really rich structure in like involving like rotations on a helix representing numbers. It's like very intricate, and I think they did a lot of like really deep analysis on this one. Binding vectors, another great one, I think is really related to what we were talking about with inhibition heads and like kind of like selecting, inhibiting like specific like positions in a sequence, although without using like absolute or absolute position. So this involves like a mechanism where models will like tag tokens in a sequence with some direction in space, and then the model can then later like look for the item with the like triangle tag or something like that, or the square tag, like whatever it is that they're looking for. So this is like, yeah, just I think this is a great, really interesting analysis that generalizes really well to other models. Another good one is circular representations for days of the week, months, again, we talked about those, and years. So this is another example of like a multi-dimensional feature. So not just a single like direction in space. This is like a kind of like repeatable structure that shows up. And I think like it's weird to me that this is the most efficient way for a model to represent this. And I think is worth thinking about.
I think you can prove a theorem that's like in simple settings that days of the week should be cyclic like this. So like if you, basically the days of the week are a modulo system, right?
Right.
A period of 7. So, and Monday comes after Sunday just as much as, any other day of the week comes after any other day of the week. So like if you construct the adjacency matrix of which day occurs after every other day, you get a cyclic graph. Its Fourier modes are sines and cosines. So you project it into 2-dimensional space, you'll get this kind of stuff.
That's interesting. So is that something that, do they should talk about that in this paper actually?
I don't know. Yeah, I haven't looked at the paper in detail, but you can prove that that will happen in like a 2-layer linear model.
Oh, okay. That's very cool.
We had a PNS paper, we showed that like back in 2020 or something like that.
That's super interesting. Nice. Okay, that makes sense. So yeah, just to quickly recap. So I think there's like a good argument for doing circuit level analysis, which is typically extremely fine grained and can often like, you are looking at very small components in a network. So attention heads are maybe like even larger than you would typically look at. So you could look at neurons or SAE features or cross-layer transcoder features, things like that, that break up the computation like a lot. But doing this kind of analysis actually is leading us to a higher level like understanding and like helps us find like really rich and interesting structure. And I think is generally giving us like a good mental model of like what kind of what is the computer that is a language model. So just to go over some challenges and like future work. Finding this rich structure is hard. Like a lot of these papers are like super manual, and we're just people coming up with like very specific creative experiments to like find these. So in the Engels paper, they like come up with like circular probes to like look for these things. The days of the week representation. And I think there's like
in the Tegmar work or like some of the other works where they found these low-dimensional reps, how did they know where to look in the big network?
So, like both the calendar one and the arithmetic one. So I don't think I can recall like how they started that analysis, and I'm not sure if how they wrote it in the papers, how they started. But I think often one way to do it is to start taking a PCA of the representations. If you can average out like all the semantic content from a bunch of examples and like PCA it, that's like one common way to get started with this kind of thing. That's actually how I think actually exactly how I just don't know about this one, and I think this one is similar at least. But I think that's like experiment 1 in this paper. I just don't know about this one, yeah, similar stuff like that. Yeah.
Did you say whether these were on sort of just quote unquote pre-trained models, or what happens if you include some reasoning RL type fine-tuning?
Oh, yeah, okay.
You find different circuits?
Good question. So at the circuit level, I don't have like the most thorough answer because I just don't think there's that much work on it. But so there is work on, I would recommend checking out the, there's actually a few on this. So at the feature level, there's a paper, I'm blanking on the name or the first author on that, but comparing SAEs trained on the base model to a post-trained model. I'd not RL'd as far as I know. I think it was just SFT and RLHF or something. And the SAE basically transfers very well in that setting, where the like same features fire before and after. So I think there is a good reason to think that they stay pretty similar. The Nikhil Prakash, so I mentioned to a question earlier on what like fine-tuning like enhances like existing circuits. Basically finds like fine-tuning doesn't change the model too much, in at least in a limited setting. And then Ekdeep, who's coming in on Thursday, was today's Thursday, next week, was on a paper. The title was roughly like fine-tuning is a wrapper over models, which makes the argument that fine-tuning is changing a small number of parameters or changing the model in a slightly superficial way. So I would venture to guess that the circuits are mainly staying similar. One last recommendation is the cross-coding work from Anthropic. Also looks at comparisons between a base and fine-tuned model.
Yeah, I think so. I think I've heard similar things, although I've heard it as kind of a problem. Like it's unfortunate to do this extra reasoning step, and it's not really
right.
updating the model in a way that it can later.
Like you'd like it.
Like the Berkeley model is not really improving its.
Yeah, you
just changing the probabilities that come out of it.
Mm-hmm. Yeah, totally. So you'd like the model to you'd like to do RL, this very expensive RL process on your model, and it comes out with all these new exotic capabilities, but it just doesn't. Yeah, I think in some sense that's a bad thing. I think that's also really cool and interesting. Like the model has learned everything in pre-training. Like it's so smart from just pre-training. We just have to kind of pare it down to the things that we care about and encourage the things that we care about and demote the things that we don't care about. But yeah, just the fact that massive pre-training at scale produces models like that is I think exciting that we don't have to do too much more to make them much smarter. Optimistic perspective on it. Yeah. Someone else have their hand up or okay. Yeah, cool. So defining the structure is very hard. In some kind of currently wrapping up work at Goodfire, in a project with Surya, who's back there running the camera, we were looking at decomposing weights directly into shared and basically unshared, kind of unique structure that's only used for a few tasks. So this involves a decomposition ordered basically by how much the loss curves around these weights, and finding basically tasks that use the more shared structure and tasks that use the more kind of bespoke structure. And so we can find behaviorally, if we were to edit out these kind of unique weights, things that are not used most of the time, quote unquote, you can see a nice gradient where logical reasoning tasks use this kind of shared structure a lot, and memorization, so there's verbatim memorization from the pre-training data and arithmetic tend to take more of a hit when you remove these. So these are using to some extent weights in the model that are not leveraging these kinds of shared structures that I've been talking about. So we kind of draw this as a spectrum from common circuitry. Logical reasoning uses more of there's at least more redundancy for doing logical reasoning tasks. Fact recall is somewhere in the middle, because it's kind of you're recalling exact facts from the pre-training data, but maybe these show up in many different paraphrases. Arithmetic, a little bit more unusual than that, for obvious reasons maybe, and then possibly partially memorized, 2 + 2. And then memorization is the lowest on the rung, which is that the most bespoke circuitry goes to memorizing individual training examples. Yeah, so I won't go too much into that, but
Define memorization.
so in this example, in this paper, we use a few different definitions. The strictest is if you do greedy decoding, you will exactly generate a long suffix from your pre-training data, so like 60 tokens or something. And then the slightly looser one is if we were just to generate and then take the Levenstein distance, are we roughly close? Are we a small edit distance away?
Is this result good for
sequences that were memorized, you find, under that definition, you find bespoke circuitry to implement that?
So we would make the argument that like this is like circuitry very broadly construed, like just directions in weight space across many layers that are, this is not a circuit analysis paper to be clear, that are like essentially unimportant for many data, but they are very important for like specific like data, like for exact memorized points. So like the curvature example here is that this might be a direction in weight space which if you were to kind of like wiggle it locally, the loss doesn't change for most data that you put in, but it would change very quickly for a memorized point. But on average, doesn't matter very much.
So loss curvatures, are you attributing back to the data, or?
We're not actually. So we're approximating Hessians of the weight matrices, of the loss with respect to the weight matrices. Yeah. But
What? So, okay, I guess I'm asking you actually questions about what you actually did, but
no,
do you
that's
not
fine.
want to cover what you did, or?
I know, I'm happy to. I just thought I didn't think I'd have time to, but yeah.
Why don't we finish, and then if we have time, let's go back to this.
Yeah, sure.
I'd love to understand.
That'd be great. Yeah, so I think some future work on this. So one big challenge is like for some of the circuits I was talking about in this paper, in this talk, we're like working at the attention head level, and that just happens to be a nice abstraction for what we're trying to do. Attention heads sometimes are a good level of analysis, but there's just no guarantee of that being the case. So representations and structures can be distributed across layers, or possibly even token positions in the sequence. And we just don't really have great tools right now for dealing with that. Although there's work improving on that. And I think there's also like really good opportunity like for automation here. So language models are getting better at just doing scientific work and just automating like fleshing out the search space for these types of questions. So I think there's a lot of cool work that could happen there. Yeah, and I think it's also, we talked about like syntactic processing and like language learning a bit. I think that's actually why I became interested in doing interpretability. You can learn a lot about the data that you are training on by doing interpretability, I would argue. And I think there's a really great opportunity in doing interpretability, this kind of analysis, to scientific models like those trained on DNA or proteins. I think, yeah, we might just discover something new about those scientific fields, which is something that we're doing at Goodfire. So interpretability is a pretty young field. There's a lot of stuff like to do, and you can definitely contribute. Like, you can just open up a collab and start going. Again, a lot of these results I showed were in GPT-2 small, which I found very interesting. But you don't need much compute really to like start doing interpretability. But if you're very interested in this, Goodfire also has a fellowship program, so we're hiring research fellows to work on this with us. So yeah, that's it.
We actually have we have like 13 minutes for any questions.
Yeah, I had a quick question. As you mentioned here, a lot of these analyses are on like smaller models. Just wondering, as we keep scaling, multiplying a lot of these long-term models, do you feel like these type of strategies of finding circuits, etc., is going to translate well to those kind of skills?
Yeah, that's a really good question. I am like for sure giving a slightly antiquated perspective on circuit analysis. I mean, antiquated meaning like a year and a half or like 2 years or something. But so there was a paper like, can we do this analysis at scale? It requires just a lot of like ablations and like counterfactual. There's just a lot of forward passes basically. There's work on for like path patching naively. There's work on doing like gradient attribution to kind of speed this up. That scales typically quite well. There's a paper specifically on does circuit analysis scale. They look at a 7 dB model. That's, I think, not exactly what your question is getting at. You're talking about basically in the limit. So I don't think it will have the same form, like this type of analysis. Even already it doesn't have this kind of form. You just learned about circuit tracing, for example, which is another perspective on how we can do this kind of thing at scale. But even then, there are dimensions in which like you kind of want a more distilled representation. So I think there's a lot of room for doing, improving the tools we have to do low-level analysis, maybe like mid-level analysis. I think long contexts, like interpreting long contexts, like over the sequence dimension, basically is a large challenge in interpretability. For example, I won't speculate too much on like numbers, but like when DeepMind and OpenAI were competing in the Math Olympiad or like these coding challenges, they are like, there are very long chains of thought in those models, probably multiple chains of thought, like many tokens, right? Like, and we just don't really have interpretability tools to start even like analyzing something like that. We can analyze really large models over like short time sequences, but I actually think like we just don't even have the right tools to like digest what's happening over a very long rollout. So one worry is that we just get completely washed away by one mega chain of thought, basically. So in that way, I think like there's I guess multiple ways to answer that question, which is like there's ways it does scale well and ways that it really just does not. And even if it did, we have trouble like making sense of the results, basically. So maybe that's where language models come in. I don't know. Yeah. Another one?
Yeah, I would just love to hear more about your ICO paper on the loss curvature for memorization.
Sure. Yeah. Let's. So I should have prepared extra slides. I actually was really pessimistic about my timing.
Use the board. We have a whiteboard.
Oh yeah, true.
If you
Okay.
want.
Yeah, thanks. That's a good reminder. So basically, we have if we have a weight matrix W, I think everyone can see this. This has like activations going into it. So let's just say this is like our linear layer in a transform is just this one matrix or something. We have activations going into it A. Let's just call that A. So this is some vector A. And then during the backwards pass, we have a gradient vector on this side, kind of like on the outputs, the gradient on the output side of this weight matrix. So this is backwards pass G. These are both vectors. And the idea is basically if we take the covariance matrix of like a bunch of activations for A, so we just take like, let's just call that matrix A, and then for G we do the same thing, same data. We just get the covariance matrix for all the G's on the output side. Once you have that, if you take the eigen decomposition of these covariance matrices, you have the uncentered PCA of your activations and your gradients. So you can imagine like the top principal components, like of activations, just stick with those, tend to be interpretable. That's just if you cluster any data, take the PCA, that's what you tend to see, right? This is corresponding to like sort of directions of high variance in the activations, and then correspondingly on the gradient side. So the idea is basically to take advantage of this fact, which is explored in the KFAC paper. So this is a paper from 2015 by James Martin and Roger Gross, which says that the Fisher information matrix of this weight matrix, which in a cross entropy loss model is a good approximation for like curvature of the loss landscape. This will give you basically, sorry, let me back up 1 second. This is the Kronecker product between activations covariance and gradients covariance. The idea here is that we can connect this to memorization and reasoning through prior work connecting loss curvature, which is represented by this, to memorization. So maybe that's a couple jumps, but basically we can decompose this weight matrix using this approximation. We never have to actually instantiate this like giant matrix, and basically take the decomposition. I won't write it out because I don't want to add too much to this board because I think it's already a little confusing. But we can find like directions in weight space using these very easy to find matrices, the activations and the gradients, that correspond more to common circuitry or bespoke, less common, like unshared, like directions in weight space. Tell me where I can explain that better.
I think, how does the Fisher information matrix play into it? I got a little bit lost there.
Yeah, so, okay. The idea there is that there's a lot of, this is, building on, I think, like a lot of, like a long chain of work. So it shouldn't necessarily be obvious, like, what this means, but the idea is that we can, with the Fisher, we get a good approximation of, like, let's say we have the loss L and some, like, weight direction. The loss curvature basically tells us like how flat is this basin here versus here, right? Sorry, this isn't very big. The idea here is that like how sharp or flat like the loss is in some direction can tell you something about whether this is a memorized data point or not.
And how does this speak to whether there's like shared structure across transformers?
Yes. So the idea there is that if you take, so these are basically averages over data, right? So we talked about this is a bunch of activations, it's the covariance matrix. This is a bunch of gradients, the covariance matrix, right? So when you sort of like average these things together, if there's one direction in the loss landscape, so this would be the direction, right, which has very sharp curvature for like one data point, like it's a memorized data point, it tends to be flat for all other data points, or not exactly flat. There's a little bit of a simplification, but tends to be flatter for most data points, versus directions that are used a lot by many examples. So for example, I will just make one up. We don't talk about this in the paper, but like, let's say there's a direction in weight space representing an induction head, used all the time. If you messed with that, that would like perturb the loss maybe a little bit for a lot of examples. So on average, this would have higher curvature. Like this would show up as like a top, if you were to eigen decompose A or G, this would show up basically as a top component in the eigen decomposition, because it's more variance. Yeah, I see heads and hands a little bit. Yeah, so I think that's a bit of a yeah.
It looks like the paper is on open review, right? So we can read it. I mean,
yeah, go crazy.
That you've done that isn't in the paper. That's
No, nothing in the paper. Yeah. But yeah, I think that the main thing I would stick to. I think it's maybe not super helpful to stick to like why we're doing what we're doing. The main thing is that we want to collect these A's and G's, and like following the same kind of logic as like top principal components are like explaining a lot of variance in data. We can like similarly explain a lot of like behaviors in the weight space using this. Maybe I'll write out one more thing, which is if you were to get the eigenvectors for A and G. So if you have, let's just say you have some eigenvector. I shouldn't use A because that's my activation. Like U for A. So this is eigenvector. And V from G. It's another eigenvector from G, the covariance. Again, some principal component. Their outer product is going to be the same shape as this weight matrix. Or rather, it'll be, well, yeah. Anyways, you can view it as like a kind of slice of this weight matrix. And that's the kind of thing that we're like editing out. So it gives us like an editing procedure, basically. We can edit out top components from this product or bottom components. Bottom components being those like very flat directions, which we're arguing are used for like memorization and arithmetic and stuff. Because they're perhaps sharp just for those data points, but like kind of flat everywhere else. So yeah, anyways, this gives us a way to project these out. And that gives us these selective edits let us like test behaviorally which like benchmark type tasks like respond poorly to that kind of edit. And so we're able to draw this spectrum between memorization and reasoning.
So the memorization you're saying is more brittle.
It's more brittle, yes, exactly.
Very interesting. I think I only follow up a little bit, but all that information.
Okay, yeah, I think yeah, that I think it's a difficult thing to. There's a lot of background. Yeah.
Could you tell us about what Goodfire is doing with scientific models?
Sorry, can you repeat that?
What Goodfire is doing with scientific models? I mentioned it there.
Yeah, sure. So we are largely looking for like structure and like to some extent like, well, ultimately we'd love to find like models that have ingested tons of data, have learned like from this data things that we wouldn't have picked up on because we just can't ingest that much data, right? So like we'd love to look for like clues that like a model using a like novel scientific principle or some like signal from the training data that we just haven't picked up on. So for in DNA, this could be like genetic markers for some disease or something that we just didn't know were good genetic markers. There's a paper that we wrote with the Arc Institute earlier this year where we looked at their nucleotide level like model, and in that paper Goodfire trained an SAE on their model and found a direction in the activation space corresponding to I'm going to get it wrong, this was a little bit before I joined, some marker for I think it was an exon sequence marker or something like that, and they were able to use that like activation of that feature to like annotate an unannotated like genome for these like sequences. So things like that, tools for basically like processing data with these models and novel discovery.
We should probably stop here because we're over time. So, but let's thank Jack.